Good morning, ladies and gentlemen. May I have your attention, please? Thank you. At this time, I'd ask you to raise your hand if you do not have a red mark for today, the 2nd of November. Great. Quick reminder, we have the quiz second half with exponent properties, and the questions look very similar to these 5 Bellwork questions. So let's go ahead and get started right now. We know that if there are no parentheses, right, if there are no parentheses, then an exponent only applies to the factor directly next to it. And so in my first power, the green power, 4x cubed, we know that the 4 is not raised to the third power, only the x's, and so on and so forth. So we can go ahead and multiply 4 times 7 equals 28. And x cubed times x to the 11th. We remember our shortcut operation for multiplying powers together is to add the exponent. And so x to the 14th. So raise your hand if you had 28x to the 14th. All right, I had 28x to the 14th. That's great. So that's very similar to a quiz question. Let's take a look at number 2. If there are parentheses, then everything inside the parentheses is raised to the exponent, which is why this first power, this green power, negative 3x quantity squared, everybody gets squared. So negative 3 times negative 3 is positive 9. X squared is x squared. I'll go ahead and apply my exponent of 5 to my product, 2xy, and everybody will be raised to the 5th power. So 2 to the 5th, x to the 5th, y to the 5th, and now we can go ahead and group. My 2 to the 5th is 32 times the 9 would be 320 less 32. So what would that be? 288. 288. Great. So we get 288. X squared times x to the 5th is x to the 7th, and then the y is by its lonesome. It has nobody else to combine with. It'll still be y to the 5th for my final answer. Please raise your hand at this time if you had 288x to the 7th, y to the 5th. Did you already have that? Good job with the parentheses. Now let's go ahead and take a look at number 3. In number 3, we're going to simplify an expression that includes a negative exponent. And so anytime we have a power raised to a negative exponent, it doesn't mean, right? It doesn't mean negative answer, it means reciprocal. So we'll grab onto that power and rewrite it with a positive exponent by hopping the line and changing the sign. That is, hop the line of the fraction bar and then rewrite with the positive exponent. So we'll go ahead and grab onto that y to the negative 6th power, and we'll hop the line and change the sign. That's equivalent to y to the positive 6th on bottom. In the meantime, we can do some simplification with my my numbers. 3 and 18 share a common factor of 3, so I'll go ahead and divide that out on the way. That would be 1 x to the 4th over 6 x squared. My y to the negative 6th is going to jump down to the bottom and become y to the positive 6th. And then we still have our y cubed that was there originally. So as everybody see, we've reduced the common factors in the number. We've hopped the line and changed the sign of the y to the 6th, and the y to the cube is already there. So far, everybody good? Yep. Now let's go ahead and see if we can simplify this a little bit more. I know that I have common x powers here, so do I have more x's on top or on bottom, Olivia? By how many?
2.
Good. So my final answer will have x squared on top, we'll have a 6 on bottom, and then how many y's do I have in all on bottom? Logan? 9, so y to the 9th. So my final answer is x squared over 6y to the 9th. Raise your hand if you already had that. So if you already had that, great work, you guys. Thanks, hands down. Awesome. What questions do you have about the first 3? Okay, then let's take a look at number 4. The entire quotient, right? Both numerator and denominator is raised to a negative exponent. So we've got a couple ways that we can handle this. We can apply the negative exponent to the entire quotient first by flipping everybody inside and rewriting to the positive, or we could simplify our inside quotient first and then apply that negative 3 exponent on the outside last. I think it'll be simpler to simplify inside first, and then we'll make an easier fraction, and then apply to my outer exponent, the negative 3 last. So let's go ahead and leave this as a quotient to the negative 3rd. But on the inside, let's do some simplifying. And so we'll go ahead and rewrite my inside 5a cubed. And we'll grab onto this b to the negative 5 exponent and hop the line and change the sign. I know that a b to the negative 5 on top is equivalent to b to the positive 5 on bottom. Similarly, I know that a to the negative 2 on bottom is equivalent to a to the positive 2 on top. So we've grabbed on those powers with negative exponents, we've hopped the line and changed the sign. Meanwhile, back at the hacienda, we still have that original b chilling on the bottom. Does everybody see it? Okay, so let's go ahead and reduce our inside quotient first, and then still apply to that negative third last. So here we go. I'm going to rewrite this as 5a to the 5th power, so 5a to the 5th power, over b to the 6th power, and now we can apply our negative exponent, bless you, last. This entire quotient is raised to the negative third. Does that mean negative answer? No, it means reciprocal. So we'll go ahead and rewrite the inside quotient as the reciprocal and then raise to the positive third. So it's no longer 5a to the 5th over b to the 6th, it's now b to the 6th over 5a to the 5th. Awesome. So if a quotient is raised to the exponent, this exponent 3 outside, does the numerator or the denominator get raised to that exponent? Katie? It's both, absolutely. And so both the top and bottom get raised to that exponent, which is why we get b to the parentheses in between my exponents, power to a power, multiply. B to the, not 9th, but 18th over 5 cubed is 125, and then a to the 5th, all cubed is a to the multiply exponent, 15th. So a to the 15th. So put it all together and we get b to the 18th over 125, a to the 15th. What question do you have about number 4? Carson.
Should it be a negative 3 to the power?
Great question. So negative 3 to right where?
Like before you got there.
Right here?
Yeah.
Okay. So how do we get from this line in green, right, to this line in blue? We apply the negative to the base. So we flip the base and then rewrite to the positive. Does that make sense? So we used it up. We used it up in our reciprocal of the base. Then we still have to cube it. Good question. All right, let's go ahead and finish up. In what quadrant does f of x equals negative x to the 7th appear? We know from our parent functions that x to the 7th, right, behaves much like one of our other parent functions. And so go ahead and tell the class when I'm calling you, is my exponent in this power function even or odd? Dakota? Odd. So is this going to behave like a squaring function, right, a squaring function, or a cubing function for my basic functions? Marina? A cubing function, good. And so if this had just been x to the 7th, we know it exhibit our down up disco behavior like our cubing function. However, the negative in front is going to do what to the appearance of this graph? Well, it'll take and make opposite orientation. Margot, so that's going to do what?
So like flips it to the
Absolutely. And so normally, the graph of an odd power function, right, like y equals x cubed or y equals x to the 7th would appear in quadrants 1 and 3. However, given the negative out front, my new graph is going to appear in quadrants 2 and 4. It'll be upside down like this. So it would appear in quadrants 2 and 4. Awesome. What questions do you guys have on today's bill? Bless you. Okay, let's go ahead and take care of our homework check. At this time, please take out your walking assignment number 2. Give yourself credit and pencil for those of you who completed out of yes, that's right, 58 exercises. If you showed me your reading questions for 7.4 and 7.5 as I came around, then you'll be eligible for the 5th point. If you just did one reading question, then it would be a plus 0.5. And if you did no reading questions, your maximum Infinite Campus score will be 4. Go ahead and box your Infinite Campus score around to the nearest half point. 0 to 5 on top. And take this opportunity to staple multiple pages together if you have them, please. If you need a stapler, there's one on the side activity table and one on the front table. What questions do you have about your Infinite Campus score today? Okay. Then let's go ahead and take a look at our answers. So pencils down, please. Grading pens out. We'll take a look at our answers from the first section. And to make sure we have plenty of time for your quiz, we'll advance fairly quickly through these. Are you almost ready? And 7-2. And soon we'll be advancing to the next slide. And the final section, 7-3. finishing up, go ahead and give yourself an accuracy fraction on how many you did, about how many did you get right. Make sure your infinite canvas scores box nice and big in pencil. Your name, first and last, 1A, number 2 clearly labeled. Multiple pages to be stapled together. And then go ahead and pass from back to front, please. Front row, make sure they're facing the same direction. I appreciate your help. Everybody good with assignment number 2? Assignment number 2? Okay, thank you, ladies and gentlemen. Today we're going to look and see how we can use and apply geometric sequences, right, in the arena of compound interest. We'll also get some notation, and the good news is that arithmetic sequences have their own notation, and the notation for geometric sequences is very similar. And we'll find out those, we'll be able to compare and contrast arithmetic and geometric sequences as we develop them, and then you're going to have your quiz during the second half of class. So let's go ahead and get going. So what we want to do is make sure that we're comfortable using the exponent keys on our graphing calculator. And so let's go ahead and evaluate the following expressions. What I'm going to ask that you do is go ahead and evaluate those and write down the answer. Careful of your use of parentheses, and then we're going to go ahead and check and see that we get the same thing. Okay, so go ahead and write those down, and I'm only going to give you guys about a minute and a half to do that. So the last one is the only one we really have to be careful about with our use of parentheses. We want to make sure that when we're raising that base in parentheses to the exponent 12 times 5, we include parentheses around our 12 times 5. Or if you're in math type, then it'll stay up in the exponent 12 times 5 before down arrowing. So we want to make sure that it's raised to the parentheses 12 times 5, depending upon your calculator notation. Okay. Let's go ahead and share your response then with the class when I call on you. So what did number one simplify to? Ben?
350.77.
350.77. Raise your hand if you had the same as Ben for the first one. Awesome. What did the second one, 1500 times quantity, simplify to? What did you get for that? Caitlin? 1,610.32. Nice job. Raise your hand if you had the same in blue. The same in blue. Great. What did you get for the third one then? The third one, Katie?
1,286.57.
And raise your hand if you had the same in red. You have the same one. And then lastly, with parentheses, you want to be careful with that. And what did you get for number 4 then, Adam?
13,700.
As did I. Raise your hand if you had the last one correct. The last one? Awesome work, you guys. And so we just want to make sure that we're comfortable with our exponents because in our compound interest formula, we'll have to enter expressions that look like the last one. Also recall that we can define an arithmetic sequence either explicitly, right? We're given like a function rule where we can evaluate the nth term simply by plugging in my n equals term number and evaluating it in a function rule. Or, like in letter B, recursively, where I have a start value and then apply some rule recursively in order to generate several terms using the pattern, either addition or subtraction. Let's go ahead and write the first 4 terms of the sequences defined below. And so for letter A, I know that the first term, call it a sub 1, is given by evaluating my explicit formula when n equals 1. So that would simply be 4 times 1 plus 7 equals 11. I know a sub 2, my second term, would be gained by substituting in 2 for n and evaluating. 4 times 2 is 8 plus 7 is 15. You guessed it, a sub 3 would be gained by evaluating my explicit formula when n equals 3. 4 times 3, 12, plus 7, 19. And our last of the first 4 terms would be given by 16 plus 7 is 23. While an explicit formula is useful for evaluating, right, all I do is plug in the term number into a function rule and work it out. It's quicker and easier to list the first several terms of a sequence when defined recursively. And that's going to hold true for geometric sequences, what we'll look at in just a minute today as well. Remember, my start value is always given for a recursive definition, and then I simply apply my pattern. I know the current term would be based on the previous term, and then increase its value by 3.5. So I'd start at 9 and then plus 3.5. So 12.5 plus 3.5 would be 15, 16. So 16 plus 3.5. So 19.5. Dot, dot, dot. So my first 4 terms would be given simply by adding 3.5 to each of the previous terms. What questions do you have about our arithmetic sequences? Old news? Then let's apply what we already know about notation in the arena of geometric sequences. And so what we're going to do is first do a financial application so you can see how this can be applied in the real world. And then we're going to go ahead and get our notation down for our chart, and then we'll take our quiz second half. So here we go. When interest is earned more than once a year, we use a more general compound interest formula. And so the formula that gives the amount A in the account after 2 years, based on a principal investment P, that's how much money you put in initially, at an interest rate R as the yearly interest rate for a time T in years at a given number of n compoundings is A equals P times quantity 1 plus R over n, closed quantity all to the n times T. This is the exact formula that banks use to calculate the amount of money in your account based on the interest rate APR as a decimal and the number of compoundings per year. Some banks compound, in some accounts, compound interest quarterly. Right, you've heard that, quarterly. Some compound interest monthly. Some compound interest daily. And so we're going to figure out how we can use and apply this formula to calculate the amount of money in your account after 2 years. The main thing is that you have the underline word, right? So you know what the letter stands for. And we'll do several examples of these together. Okay, so the key thing here, everything else makes sense except what might be new is the number of compoundings that occur in a given year. So if we compound interest semi-annually, right? Semi means half, like a semicircle. Semi-annually would be compounding interest every half of a year. So how many times would interest be compounded in one full year? Twice. And so semi-annual compounding would be twice a year. How many times a year would quarterly be? Tyler?
4.
4 times a year is right. How many times a year would be monthly, right? Would be monthly. Casey?
6.
For monthly, how many times in a year? No more semi.
Sorry, 12.
Yeah, absolutely, 12, thank you. And daily will go 365. To match my text speed, 24/7, 365. Those are some common bank account compounding, number of compounding periods in a given year. Let's go ahead and try some. So, suppose $5,000 is deposited in an account that pays an interest rate of 8.5%. What will be the account's balance after 1 year if the interest is compounded annually, semi-annually, or daily? In order to do this, we'll simply use our formula and plug in the given information. So I know that an annual compounding would occur just once at the end of the year. And so to calculate the amount of interest, the amount in your account A would be given by your principal investment P times the quantity 1 plus R over N, where R is your interest rate as a decimal, N is the number of times compounded in here, all raised to the N times T. To be safe, I always put this exponent, N times T, in parentheses, so that I know that the entire quantity is being raised to that. Let's go ahead and do it for annually in green. So the amount A in my account, after a principal investment of $5,000 goes in for P, at an interest rate of 8.5% as a decimal, that would be 0.085. Annually, it would be once a year. And then all raised to the NT, that would be 1 times, and it's for how long? For 1 year? So that would just be 1 times 1 is 1. Let's go ahead and do that on our calculator. So it looks like $5,425. Raise your hand if you got that. So anybody else have that? Way to go, you guys. So it looks like $5,425. And I'm going to put a dollar sign there. Let's do the same thing, but now semi-annually. So semi-annually we'll do in blue. So still $5,000 principal investment, but now raised to the quantity 1 plus 0.085 over semi-annually would be what value of N? Well, that would be 2 times a year, all to the 2 times 1. Let's go ahead and do the same thing with our calculators then. It's just that now we'll need twice a year, which means my exponent will be 2 times 1 is 2. Voila! Looks like 5,000. $434.03. And finally, we'll do it daily, where my amount A in the account after the year investment is given by 5,000 times quantity 1 plus 0.085. All over daily would be N equals 365. All to the 365 times 1. I'll go ahead and pull up the previous. And in the previous, I'm going to go... Oh. Can I go in there? I want 365 for my number of compoundings. And so 365 times 1 is 365. Let's see. $5,443.53. What questions do you have about entering in your calculator? Let's go ahead and compare then, right? We'll go ahead and compare. So using your values from before, how much was earned in each case, right? Compare that with your 5,000. Your 5,000 investment looks like 425, 434.03. And was it 440? What was the last one? Want to go? Who's the last one?
Yeah, 5,000. Oh, just the.
Yeah.
Oh wait, 443.5.
5. Awesome. Okay. So what appears to happen to your amount that you make as the number of compoundings in a given year increases? Right? What happens to the amount in your account? Logan? It goes up as well. And so we're calculating the interest in our account based on how much is currently in it. And if we continue to compound more and more times, then our subsequent interest calculations will have a little bit more right in there on which to calculate interest and add to the account. So it keeps compounding. That's why I thought compound interest. All right, let's go ahead and connect now in your chart that which we already know about notation for arithmetic to geometric. In an arithmetic sequence, we have a constant difference, addition or subtraction between terms for our pattern. So like 5, 10, 15, 20, 25. Our constant difference there is an increase of 5. That's different than geometric. In geometric, there's still a definite pattern, but it's no longer addition or subtraction. Check out this geometric sequence. 5, 10, 20, 40, 80. What's going on between successive terms in a geometric sequence? Braden?
Not when it's times 2.
Yeah, absolutely. And so we're multiplying by a constant ratio as opposed to adding or subtracting a common difference. In our recursive formula, we still need a start value. In this case, we'll call it G sub 1 for a geometric sequence first term versus A sub 1 for arithmetic sequence first term. And then a rule that will give us the current term based on the previous. The rule for geometric involves, you guessed it, multiplication instead of my addition or subtraction that an arithmetic sequence recursive formula had. Just like before, where D is the common difference, we go up or down D units from term to term. R is the common multiplier. We multiply by some number R from term to term. Braden already identified correctly that in this top sequence, R was 2 because we multiplied by 2. So in the top one, R was 2 versus in the arithmetic sequence, D was 5. And lastly, we have an explicit formula versus a recursive formula. The explicit formula, recall for A sub n, was a single function rule, where we could use to evaluate the nth term by plugging in the term number n and evaluating. For this above arithmetic sequence, A sub n would be given by the first term plus n minus 1 times d, or it would be given by the 0th term plus dn, just like in Unit 2. Let's go ahead and do it for this one. So A sub n would be given by the 0th term. The 0th term I'd have to count backwards, right? I'd have to count backwards to get the 0th term. A sub 1 is 5, if I did it the first way, plus 5 times n minus 1, or A sub n equals, what would my 0th term be?
0.
0. So it could just be 0 plus 5n. A quick check by plugging in n equals 3. 5 times 3 is 15, and that's the third term. So yes, our formulas work. We can do the same thing for a geometric sequence. In this case, g of n would be given by the first term, that's 5, times my constant ratio, that's 2 to the n minus 1. Or, if I count it backwards to get the 0th term, remember, g sub 0 is not a member of the sequence, right? It's the 0th term, it's not there, it's a ghost term. We'd have to then divide by my constant ratio to go backwards one term, just like we multiply by our constant ratio to go forwards one term. So here we go. What is 5 divided by 2? Well, that would be 2.5. Still, my constant ratio is still 2, and then raised to the nth power instead of the n minus 1. Either of these are correct, just like either of those are correct. It's a matter of personal preference as to which form you'd like to use. Let's go ahead and practice with one, and then we'll get going. So, for a geometric sequence defined recursively, it's easy to get the first several terms. Again, the first one is given for free. Everybody pick out g sub 1, my first term. What would my first term be for this recursive sequence in number 1? Mark?
5.
5, thank you. And to get my current term, all I need to do is look at the previous one, call it g sub n minus 1, and do what to it? Multiply by 4. So this would be 5 times 4 is 20. To get the next one, multiply by 4. That's my recursive pattern. So times 4 is 80. Times 4 is 320. Times 4 is 1280. Times 4 is 5,000, 5,000, 6,000.
5,120.
Awesome. What's my constant multiplier here, Carson? Yes, Carson. What'd you say? 4, absolutely, good. All right, now let's go ahead and write an explicit formula for the sequence in number 1. So let's write an explicit formula. We've got two forms, you guys. We could say g sub n is given by g sub 1 times my constant ratio r to the n minus 1. Or we could say that g sub n is given by g sub 0, the ghost term, right, that's gained by going backwards once, times r to the n. Either way is fine. In this case, perhaps this n minus 1 formula is easier for geometric sequences. Let's see. G sub n would be given by my first term, that's 5, times my constant multiplier, 4 to the n minus 1 is built in. And so one way to write this would be g sub n equals 5 times 4 to the n minus 1. If I went ahead and applied this to the third term, I would plug in 3, in for n, minus 1 is 2, 4 to the second is 16, and 16 times 5 is 80. So this works. However, I could also do g sub n equals the 0th term. By counting backwards, I'd have to divide by 4 to get the first term. So the 0th term rather. So 5 divided by 4, if I want to get the 0th term, would give me 5/4. Times quantity, 4 to the nth power. So I can do this two different ways. Quick check with n equals 3. 4 to the third is 64. Divided by 4 is 16. Times 5 is 80. So it works either way. What questions do you have about our explicit formula? Again, a matter of personal preference. All right. So the first part of your quiz then involves our exponent properties. So we'll go ahead and include a little review for our last slide, and then we'll go ahead and get going on your quiz. You should have plenty of time to do your best. I want to make sure that we're going on it in about 5 minutes. That way everybody have at least 35 minutes, and so that'll be good. So when we take two powers and
does our quiz have like recursive and explicit?
Nope, there's no sequences on this quiz.
Okay.
So when I multiply two powers together, go ahead and tell the class what my shortcut operation is with the exponents. What would we do with this 4 and this 12 if we multiply together two powers with like bases, right? What do we do with those? Taylor? Absolutely. And so 4 plus 12 would equal my exponent x, and that would be 16. When we take exponents, a quotient of powers, my shortcut operation with exponents is subtraction. So even if I have negative exponents, I can still do top exponent minus bottom exponent. So for us, top exponent 6 minus bottom exponent negative 3 would be 6 minus a negative 3. That in turn equals 9. And so y would have to equal 9. When I take a power and raise it to a power, right, my shortcut operation is multiplication. So z times 3 would have to equal 9. What would z have to be? 3. So we can see that our exponent properties can be applied through inspection in order to evaluate, right, each of those powers and determine my value of the variable.
Think of our old video again.
And lastly, let's go ahead and consider the product, right? The power of a product. The power of a product, everybody in it gets squared, and so 13 negative 2 squared is positive 4. X cubed squared. What's my shortcut operation between exponents when I raise a power to a power? Eric?
Multiplication.
Good. So 4x to the 6th, not 4x to the 5th. Good job. Number 14, negative 2x squared all cubed. Everybody gets cubed. So negative 2 times negative 2 times negative 2 is positive, negative, nope, is negative 8. X squared cubed is x to the 6th again. So this time we have a negative 8x to the 6th. In a quotient, who gets raised to the exponent? The numerator or the denominator? Adam? Both. And so this becomes p to the 7th over q to the 7th. In a product, who gets raised to the exponent? They both do. And so everybody gets cubed. That is 5 cubed times q cubed over 3 cubed times p cubed. All right, let's do a single fraction. 5 cubed is 125. P to the 7th, q cubed, all over 3 cubed is 27. P to the 3rd, q to the 7th. And lastly, we'll go ahead and reduce. 125 and 27 do not share any common factors, so I'll still have 125 on top, and I'll still have 27 on bottom. However, my p powers, p to the 7th and p cubed, are a common base, so we can reduce that. Do I have more p's on top or on bottom? Katie?
On top.
On top by how many? Good. So my final answer will be p to the 4th on top. And do I have more q's on top or on bottom? Aaron?
Bottom.
Bottom by how many?
4.
So q to the 4th on bottom. And we're one to go. Casey?
Wouldn't it be like q to the negative 4th for the bottom part?
Yeah, great question. So Casey recognizes that we have a top exponent of 3 and a bottom exponent of 7. If we applied our quotient and did subtraction of exponents, we would get 3 minus 7, which is negative 4. However, that would be equivalent to a q to the positive 4 on the bottom of a fraction. And so if you wrote the q on top, then it would be negative. For your quiz, please only put answers with positive exponents. So don't leave anything with a negative exponent. It's fine to get a negative exponent along your simplification, but at the end, you should rewrite positives. Great question. And one to go. Notice how the negative 5 is inside the parentheses. So it doesn't apply to the 7, it only applies to what's right next to it. So when I go ahead and rewrite this, I get 21b times b to the positive 5th over 7 times 6 times b to the 5th. So it looks like my b to the 5th and b to the 5th cancel each other out, and I get 21b over, and then 7 times 6 is 42, which will result in a common factor of what? 2, so 1, so b over 2. Is that it?
Yep.
Awesome, you guys. What questions do you have about our discussion today? Carson? Pardon? The 1 right here?
Yes.
You could, but I won't let, yeah. You could, but you don't have to have a coefficient if it's 1. Great question. Other questions about your review?
So the exponent will be the.
Okay, ladies and gentlemen, at this time I ask that you take everything off your desk except for a pencil and your calculator. I'm going to go ahead and stop the recording.